Modern theoretical physics currently faces a systemic epistemological crisis, driven by an over-reliance on ex nihilo construction. Ex nihilo construction is the mathematical assumption that coherent physical structures can be erected from an absolute void, using ungrounded, arbitrary axioms. When mathematical frameworks push raw integers blindly into continuous manifolds, they force physical systems to begin in medias res. At extreme scales, pushing discrete data into these ungrounded continuous spaces generates chaotic computational noise. This intense geometric resistance is known as Nash-Moser topological friction. Nash-Moser topological friction is the exact mathematical shredding of a function's smoothness that occurs when rigid, discrete constraints are forcefully embedded into a smooth manifold. The chaotic, irrational decimals observed in forward projections function as a visual decoy, masking the underlying geometry with floating-point approximations. To resolve this geometric obfuscation, an apophatic reversal physically strips away the continuous geometry to observe the back end of the mathematical flow. Understanding systemic architecture requires abandoning forward-only predictive utility and extracting geometric structures by looking backward toward the exact origin states. This reversal is executed through the posterior phase revelation. The posterior phase revelation is a formalized topological extraction that forces the observer to analyze the posterior or back end of a manifest equation. This diagram illustrates the mechanics of the operation. Feeding continuous coordinate outputs backward through an inverse boundary operator bypasses float-point distortion. This executes a reversal, unzipping the transcendental camouflage, peeling back the opaque continuous wave to reveal the rigid, discrete lattice hidden underneath. The operation retrieves unblemished discrete structural DNA, the pure integers and golden rational convergence, directly from the continuous output. The continuous manifold encapsulates the underlying integers as topological tension without destroying the original structural integrity. To trace the generation of this noise, we start with the discrete phase roots. These roots are derived from the algebraic modality of a contiguous Fibonacci integer sequence. Applying standard polynomial factorization yields two precise numeric values: the unit phase root, exactly 1, and the golden phase root, 21/55. This chart shows the forward projection mechanism, where rigid, discrete Fibonacci roots move into a continuous one-dimensional plane. The continuous transcendental manifold of the sine wave stretches these exact integer inputs, mapping them into continuous space as the fractional outputs, 8.41 and 3.7. The structural perfection of the integer states is hidden behind these floating-point approximations. Forward-only mathematical frameworks mistake this geometric stretching for systemic chaos or data loss. Executing the Splendor of the ass operation bypasses this float-point distortion by looking at the posterior of the equation. This graph illustrates the specific tool for this reversal, the arcsine inverse boundary operator. Instead of pushing numbers deeper into continuous space, the operation feeds decimal outputs backward through the arcsine function, stripping away the metric curvature. The operation retrieves the exact 1 and 21/55 integer states with zero topological loss. Retrieving these precise roots demonstrates how mathematical mass is preserved during phase shifts across continuous and discrete boundaries, a principle defined as the law of conservation of modality. This law dictates that apparent systemic losses are captured and stored as tension between topological frames. Why does the inverse boundary operator extract these specific roots successfully, while forward polynomial sequences encounter analytical breakdown? The lattice rectum paradox asks, what segment can freely rotate inside a parabola? Segments exceeding this minimum width strike the walls and wedge into place. Similarly, transcendental functions act as ancestor contexts with hard mathematical boundaries. The arcsine function is strictly clamped to approximately 1.57. When a value exceeds this filter, it triggers a failure of surjective invariance. Surjective invariance dictates that if a topological mapping fails to cover its target space, it cannot achieve compact closure and functionally leaks to infinity. Discrete roots that exceed the 1.57 limit of the ancestor context, such as 3455, mathematically crash into this boundary. A mathematical space's capacity for dynamic operation is dictated by its narrowest topological choke point rather than its infinite open ends. The splendor of the AS operation succeeds because it utilizes roots that fit within the required boundary limits. Both parent discrete roots, 1 and 21/55, are smaller than the 1.57 limit of the ancestor context. Because they fit perfectly within this filter, they smoothly navigate the topological choke point and achieve surjective closure. Successful closure requires neutralizing the axial twist. The axial twist is the primordial geometric asymmetry, or inherent handedness, of a continuous mathematical space. Surviving the ancestor context filter establishes parity-even closure. Structural stability and harmonic invariance depend on perfectly neutralizing this spinorial tension. What occurs to the heavy roots that fail the boundary filter and are ejected from the one-dimensional real number line? These ejections are managed by the winding genesis cybernetic operator. Winding genesis is a computational mechanism that forces the introduction of an alternating sign into a sequence polynomial to trap topological tension. When a mathematical relation exceeds a boundary, the system forces a modality shift to prevent data from bleeding off into computational chaos. At the not-infinity boundary limit, the system executes a 90-degree spinorial twist to resolve the geometric obstruction. This twist reroutes the ejected root through a hyperbolic trapdoor, shifting it out of continuous real space directly into the hyperbolic complex imaginary plane. The topological tension generated by the limit is conserved across the real imaginary boundary. The universe's structural grammar is anchored by discrete integer bounds. These bounds remain preserved beneath the continuous geometry of spacetime, awaiting exact topological extraction.